Now come to the grouping of capacitors or calculation of effective capacitance. Grouping of capacitors. So, in the grouping of capacitors, we are going to calculate the effective capacitance if the combination of capacitors are given C. So, what is the meaning of grouping? If we are having set of capacitors, suppose 2, 3, 4, 5 capacitor, and we want to replace all such a capacitor with a single capacitor, then how to calculate the effective value so that there is no effect in the whole circuit? The first, we can say we are having a series grouping. Series grouping means all capacitors are connected in such a manner that charge on each of them are same, or no branches originate between the two capacitors like this. See, suppose this is your 3 capacitors. A and B are the point across which these capacitors are connected, and we want to convert or we want to replace these 3 capacitors with a single capacitor. It means our objective here, if we want to replace these 3 capacitors with a 1 capacitor, so what could be the value of this resultant capacitor? That is called your C equivalent also, or C effective, so that whatever the charge on all these 3 capacitors, that should not change. So, first thing is that how to identify these are in series. So, series means we can say if there is no interconnected branch between the 2 or more than 2 capacitors, then we can say these are in series. See, so effective means if I am joining, if I am connecting the ends of these circuit with a, let us cell of EMF E, and through cell at steady state let total charge Q flows. So, when Q charge flow, so that Q charge will appear on these plates like this. See, charge on each of the 3 capacitors will be same. So, that can give you an idea कि okay, these are in series. So, meaning of that, all these things if we are replacing with a single, and if we are connecting this with the same battery as here, then also charge should come how much? Q charge. So, then we can have all these 3 can be replaced with a single capacitor, and that single can be said as a equivalent capacitor, and its capacitance is called equivalent capacitance. How to use? Just use this second law of Kirchhoff. I am going from in clockwise direction. Let I am starting from A and I will come back at A again. So, if I am starting from A, then we can write like equation minus Q by C1, then here minus Q by C2, minus Q by C3 plus E, which is 0. Then we can write Q 1 by C1 plus 1 by C2 plus 1 by C3, which is equal to E, is the first equation. Similarly, the same Kirchhoff law we are applying here. Then see how to get minus Q by C equivalent, minus Q by C equivalent plus E, this is 0. Then Q by C equivalent is equal to E. See from the equation first and second, see the similarity. Absolute similarity is there if we are writing 1 by C equivalent is equal to your 1 by C1 plus 1 by C2 plus 1 by C3. So, we can see from equation 1 and 2 we can have the result 1 by C equivalent is your 1 by C1 plus 1 by C2 plus 1 by C3 It means if we want to calculate what is the effective value of capacitance, then we can get effective value by using 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. This combination is called your series combination or series grouping. Now see the next is the parallel grouping. Next is the parallel grouping. In parallel grouping means when the capacitors are connected across a common points like this. So here we can say all the three capacitors of their capacitance, let C1, C2, C3, these three are connected across the same 2 points. So A and B capacitor C1 connected, between A and B C2 also connected, between B and A C3 also connected. So parallel grouping we can say either all the capacitors are connected across same points or potential difference across the capacitor should be your same. So here again I want to replace all these three with a single capacitor, and that single capacitor have capacitance let C equivalent. See, same method. It means if I am connecting this terminal of a capacitor with a source of EMF E, similarly here also source of EMF E, then if the source of EMF is delivering or flowing the charge Q, and that charge further divide let into 3 part. So in the effective cell here also charge should be your Q. This is the meaning of this. The first, by using Kirchhoff first law, as Q charge enter, it distribute into 3 part. So according to first law of Kirchhoff, so whatever charge enter that is distributing. So one equation we can say Q is equal to your Q1 plus Q2 plus Q3. This is the first equation by using Kirchhoff first law. Now we can apply Kirchhoff second law. First we can take a outer loop like this. If we are moving through the outer loop, I am starting from here, that can be written as Q1 charge is coming. So here Q1 charge, here Q2 charge, and here Q3 charge. If I am going through that path, we can write here minus Q1 by C1, then cell E which is 0. So this written as Q1 is equal to C1 into E. Similarly, if we are applying Kirchhoff's second law in the middle branch and Kirchhoff's second law in the lower branch, so what we will get, Q2 is equal to C2 into E and Q3 is equal to your C3 into E. Let this is the equation number 2. Now from the equivalent diagram, same thing we are doing here. Now we are applying Kirchhoff law here, and here the same charge Q will appear. So minus Q by C equivalent plus E, this is 0. So Q is equal to your C equivalent into EMF. This is your third equation. Substitute the value of Q1, Q2, Q3 and Q from second and third equation into first equation. So from equation 2 and 3, substitute the value of Q, Q1, Q2 and Q3 in equation 1. So what we will get? We will get C equivalent is equal to your C1 plus C2 plus C3. So this is your net result if these are in parallel combination. So parallel means capacitor should be connected across a same common point, or potential difference between the capacitors are same. So these two relation, one is the series grouping and another is the parallel grouping. It will help to calculate the equivalent capacitance. See the application of this series and parallel grouping in the calculation of equivalent capacitance. See.